conjecture by Lagrange is the following. For every discrete model, there exists a function called Lagrange functions, L, which is a function of Q dot and T. So you need to know the instantaneous configuration, the instantaneous Lagrange velocity, Q dot is nothing else than d over dt of Q1, d over dt of Qn. Okay, and to this triple, we associate a real number. Okay. From such that we can formulate the principle of least action. Okay, now I need to tell you what is the principle of least action. Okay. Don't ask me how we discover L. There is no way for discovering it. You must invent it. It is a conjecture. Okay? This is a basic assumption of your theory. Now we go to the principle of least action. The motion for a Lagrangian system minimizes the action functional. What is the action function? Is a mapping which for every function belonging to the class C2 associates the integral built with the Lagrangian function, which we have introduced before. Okay. So the principle of least action is a principle which teaches you how to calculate the motion for a Lagrangian system. It tells you that the motion of a Lagrangian system minimizes the action functional. Why we call it action functional? Because this is a new kind of function. It is a function which maps functions into real numbers. The reason for which I wrote here Q with the dot here is that I don't want to make you believe that this is an element of Rn Q of t. It is a configuration of the instant t. I wrote Q with the dot inside for meaning that the action functional depends on the whole function Q in the whole interval t0, t final. Now, before we proceed, I must tell you that the formulated principle up to now is incomplete. So it is not completely formulated, and I want to explain you why. Okay, via some examples. So let us choose for analogy. This is an analogy. Okay, let us choose the function y equal x squared. Okay, imagine that I tell you that I want to calculate the minimum of this function. Okay, everybody will say what you are telling. The minimum is 0. Okay. Why? Because you are implying, without telling, that you are looking the minimum in the set of the whole real numbers. If instead of finding the minimum in the whole set of real numbers, you choose the minimum in the set a plus infinity in this interval, then the minimum is a squared. Okay. To be even more twisted, we have already spoken about real numbers and rational numbers. Imagine that you have in the set -1 plus 1, the set of all irrational numbers. So you consider the set of irrational numbers intersected with the interval -1, 1. Okay. Okay. Then, where is the minimum of x squared in this subset? There is no minimum because 0 is not irrational. You have an infimum of the function x squared, but you don't have a minimum. You don't have any irrational number whose image in x squared gives you the minimum. Okay. So if you agree with this, you will agree that to precisely formulate the principle of least action, you need to specify precisely the domain of the action function. Okay, so we said already that Q of T belongs to C2. Okay. However, we need to further specify this domain. Okay. So in order to do this, we define isochronous we define isochronous motions. Okay, so we define two time instants, T0 and Tf. We define Q of T0 equal a certain configuration Q0 and Q of Tf a certain final configuration Qt. The set of isochronous motions start from the configuration Q0 and arrive to the configuration Qt, which are blocked. Iso means the same in Greek. Chronos is time. At the same time, they are in the same configuration. This is what this Greek word means. Okay. Okay, so now we can start writing formulas. We have Q of T, which belongs to C2 in the time interval T0, Tf, isochronous. Okay, so we could also write C2 of T0, Q0 T final, Q final. So we have every C2 function which starts at instant T0 from Q0 and arrives at instant Tf in the configuration Qf. Okay. And in this set, we look for the minimum of the action functional, which we have written in this way, using Lagrangian function. Okay. Now, be careful. This is something you have to understand. The Lagrangian function is a function from Rn, because Q belongs to Rn. Cartesian Rn, because Lagrangian velocities Q dot belong to Rn. Cartesian R, because time is a real variable. Okay, and it maps these tripods in R. So it is a real number. Now here, what you are doing in this formula, you are composing this L with the function Q of t and Q dot of t. So at the place of Q, you replace the current value at instant t. At the place of Q dot, you replace the velocity Q dot of t. And then you calculate L of Q of t, Q dot of t, and t. And this is what? This is a real valued function of one real variable time. It is the composed function of the Lagrangian with the motion and the velocity, which are both function of time. Okay? You agree with that? Okay. And the set where you are looking for the minimum is the set of functions having at instant t0 the value q0 and at instant tf the value qf. Okay. Very well. Now, how can we compute the minimum of the action A so you meet now the problem which has been solved by Lagrange when he was 17 years old. Okay, so don't try to say that it is difficult. Okay, now let us start slowly. So let us start from a simple problem, a simpler problem, which we have already solved. You know, this was the mental process which you find in Lagrange. Okay. We have a function instead of having a functional. So simpler problem means more particular. Okay. So instead of having a functional, we have a function. Okay. So we have a function which is, you have the variable t and the variable y of t. Maybe it is better if I call it x. We have a function, a variable x and y of x. And then you have this function, the plot I have drawn. How do you discover a minimum if the function is regular enough? Okay, consider that if your function is not regular like that, finding minima is rather difficult. Okay, so we assume to have a function which is regular enough. So you can calculate the first and second derivative of the function. You go in a position which is a minimum. Okay. Then you write a Taylor expansion starting from that minimum. What is a Taylor expansion? It is a polynomial which is approximating the function. Okay, so you want to find a polynomial a0 plus a1x minus x0 plus a2 x minus x0 squared. And you want that close to x0, the polynomial p2 of x is close to f of x. Okay. Now, the polynomial which of second order which is closer to f in the vicinity of x0 is. So we write this formula. This means nearly equal. Okay. It is f of x0, the value of f in x0, plus the derivative of x, of f in x0 times x minus x0 so if this is your plot, this straight line as equation f of x0 plus f prime of x0 times x minus x0. Okay. You agree, Bruno? Plus,
yes, Professor.
Plus f second of x0 divided 2 times x minus x0 squared plus infinitesimals of higher order, which means quantities which are going to zero quicker than x minus x0 squared. So this infinitesimal of higher order, of order higher than 2, in the limit when x tends to x0 tends to 0. So this quantity here is smaller, goes to 0 more quickly than x minus x0 squared. Okay? And one could also write a kind of parabola which approaches this, something like that. And it is closer than the straight line. Okay. And then you can go on. If you go to Wikipedia, you will see all these polynomials, Taylor expansion with nice drawings, so you understand in a better way this idea. Now, why it is so important, Taylor expansion for finding minima. Because when you have that x0 is a minimum, this means that this equality, this inequality, is verified when x is close to x0. Okay. So what it means? That f of x, which is nearly equal to f of x0 plus f prime of x0, x minus x0, plus infinitesimal of order 1, because you can, in this moment, neglect the second order, okay, is greater or equal than f of x0. When x is close to x0, you can forget this in the inequality. There is a famous theorem, which I'm sure you have studied, Bruno. The theorem of permanence of sign in the limit. If g of x is smaller or equal than f of x for every x, then the limit of g of x is smaller or equal than the limit of f of x. This is called the theorem of permanence of sign in the limit. So if you calculate, if you say that this inequality is verified, then you know that this inequality is verified. When x is tending to x0. Okay? Okay. Now, this implies that f of x minus f of x0 is greater or equal than f prime x0, x minus x0. But this quantity, because of our assumption, is positive. Okay? Okay? So we have that f of x minus f of x0 is greater or equal than 0. Okay? And f of x minus f of x0 is nearly equal to f prime of x0 times x minus x0. This is called the first variation of f with respect to the variation delta x. Delta x is x minus x0. Is the small variation of x0 of x in the neighborhood of x0. So this is the first increment of delta f, because we have replaced in the Taylor expansion, we have killed the extra term. Okay. So look the difference. This is the finite increment of f. This is the first increment of f. Here you have nearly equal, and here you have equal, because this is what is called the first, this is a definition. This is the first variation of f. Okay? Now, for the theorem of permanence of sign, the first variation of f in the neighborhood of a minimum must be positive. Okay? Because when x tends to x0, the finite variation and the first variation are the same thing, or at least have the same sign. Okay? Now look at this f prime of x0 times x minus x0. When this is positive, when this is negative, this first variation is negative. So f prime of x0 cannot be greater than 0. If f prime of x0 is negative and x minus x0 is positive, then again this is negative. So f prime of x0 cannot be negative. x0 is a minimum, implies f prime of x0 is 0. Or delta f calculated in delta x is equal to 0, because this is equal f prime of x0 times x minus x0. So in a minimum, the first variation is 0. This is what Lagrange generalized for the action function. And we will see in the next lecture. Okay, so please, Ivan, switch off the video. Look, Bruno, if you want, I suggest you to follow the lecture of Professor Giorgio also. Okay. So, Ivan, I give you